involved. So it is an interaction of light with the electronic devices, and that make it an optoelectronic device. Say, for example, I can give you an example of an optical emitter or an optical source. Optical source or optical emitter, which you know as a light emitting diode, is a simple example of an optoelectronic device, which is an emitter or a source of light. Right? It is an electronic device which can emit light. So this is very common. Light emitting diodes are used for display purposes and many other applications also. You know that LED has become very popular in recent times for general purpose illumination as well. But initially, it was for specialized applications, including application in optical communication. Later on, it was found that LED can be used for general purpose illumination because the consumption of electricity is very, very low when you use this, can be used for. So this is one example. Likewise, you can have an optical detector or a sensor, a photodetector, or a light-dependent resistor, LDR. So these are all examples of optoelectronic devices. Photonics, on the other hand, so there are two domains. One is your electrical domain, where we talk in terms of that electronic devices, flow of electrons. And the other one is the optical part. Light interacts with the matter and makes some changes in the electrical characteristics of the material, or that is reflected in the terminal characteristics of a device. And that's how an optoelectronic device works. Photonic device, on the other hand, should be treated as one where the domain, it doesn't change, because in optoelectronic devices, light changes to electrical domain, again electrical domain to optical domain. But when we process everything in the optical domain, then that becomes a photonic component and photonic device. There are a lot of examples where we process the entire thing in the optical domain. We never bring it to the electrical domain and process it. Right. I can give you a simple example of current technology which is used for optical communication. Right, where you'll find that the information signal which is used here is transmitted using light as a carrier. Light carries this information from one place to the other. Intensity of the light is modulated and sent to the destination point. Right. Now, in this process, you'll find there are several stages where it is involved, where you'll find that the electrical signal which you want to transmit now gets modulates the intensity of light. So it gets into optical domain. But when you process and try to get back the signal, you bring it back to the electrical domain. So there's a frequent change from optical domain to electrical domain. And whenever you do this, you have to compromise with the bandwidth. When it comes in the optical domain, the bandwidth is very, very high. And when it comes to the electrical domain, then the bandwidth becomes very small. So this is one of the major constraints of today's optoelectronic technology, which is used in optical communication. Frequent changing from optical domain and coming to electrical domain, using all these optoelectronic devices make the systems. And optical computation where all this processing will be in the optical domain. We'll never come back to the electrical domain, because as soon as you come, a bottleneck is created because of the bandwidth, decrease in the bandwidth in the electrical domain. So photonics is one, a photonic devices component is one, where all the processing is done in the light domain. So signal is received in the form of light. This is processed in the form of light. And ultimately, the entire thing is done in the optical domain is strictly photonics, right? So, for example, you can do switching using optical signal. You can have optical logic gates, which can perform all the logic functions which your traditional electronic logic gates can do. So, similar kind of function you can do entirely optical domain. Then you can imagine that how fast that system would be. So even though because of lot of practical problems, complete photonic system could not be developed. But our ultimate goal is to achieve something when you find that instead of the electrons running through conductors, you'll find that the photons running through your optical fibers and doing all these functions which the electronic circuits and devices are doing. So that is something which we are aiming at, will be a complete photonics technology. But today's lecture will be concentrating on optoelectronic devices, right? So where we'll have electronics and optical. One of the major applications of photonics is in integrated optics, IO. It is entirely a different branch where all this processing of this is done in the light domain of the signal, integrated optics. So it's similar to what we have the integrated circuits. All optical components and devices will be integrated and form integrated optics. So that is not a part of discussion today, but you know the fundamental difference between when we talk of photonics is all photonics, and when it's optoelectronics is a mixture of electronics and optical, right? So two things we'll have to, knowledge in the two areas will be required, basic fundamental knowledge in the two areas. One is to know little bit about light, optics, right? And to know about electronics. And as you know that electronics, all these electronics things started around 1904 with vacuum tubes, and during Second World War and after Second World War there is a rapid change, and the tiny semiconductor crystals are being used for making semiconductor devices, small size semiconductor devices which can perform the function similar to your old triode valves, cathode and pentode valves which were used earlier for amplification and other purposes, can be done more reliably by these small devices. So they are less bulky devices as compared to their vacuum tube counterpart. So after Second World War, it was mostly electronic devices which made a revolution in this field. Whatever development in the field of electronics has happened because of the parallel development in the field of semiconductor devices. So semiconductor devices is one of the fundamental knowledge about semiconductor devices is very, very important to understand these optoelectronic devices, and some knowledge about optics. For those who have studied +2 level have adequate knowledge about optics. You have studied geometrical optics, you have studied physical optics and electromagnetic theory also. So optics part you know, but in optoelectronic devices you need to know a little more about this, how we handle light signal. Light is something which is very, very, very interesting, and sometimes you'll think or you'll believe that probably we today also we do not know what this light is, because it is very, very deceptive, and the scientists have started from 17th century the work of Newton, the theory of light, where he said that light emitting object, so object which is emitting light, light emitters, they emit corpuscles which travel in straight line, and when there is an obstacle it casts this shadow on images, right? So shadow on the screen. So this was 17th century, the Newton's theory, corpuscular theory. And so a little bit of theory of light, let us see. We'll not get into the details because the time is very short. So we started with corpuscular theory. That light travels in straight line, and when you have an obstacle, it will cast a shadow on the screen. Right? This is simple, and using this corpuscular theory, the reflection and diffraction phenomena, which are bulk optical phenomena, could be explained nicely. That assuming that this corpuscle traveling straight line, right, which you have studied as rectilinear propagation of light. But later on, scientists found that light exhibits some other properties which probably cannot be explained with the if we assume that light travels in straight line. So then came the wave theory, which was proposed by Huygens. Wave theory, and Huygens said that this is light doesn't travel in straight line. It's basically wave motion. And there are some problem with Huygens theory, which was later modified by Fresnel. Fresnel modified the theory, and he said that light travels is wave. It's not a straight line. And there is a relationship between the size of the object and the wavelength of light. And if the size of the object is very, very large as compared to the wavelength of the light, then you can assume that the light travels in straight line. But when the size of the obstacle becomes small or comparable to the wavelength, you can no longer assume that light travels in straight line. Rectilinear propagation of light cannot be assumed. Newton was not very happy with the proposition of this wave theory, and Newton tried to give an explanation that because the two important phenomena which were observed were one was interference of light and diffraction of light. These two, corpuscular theory, you cannot explain these two phenomena. This is something related to bending of light, right? Even though Newton made an attempt to explain with the his theory that when the size of the obstacle becomes very small, at the sharp edges the ray bends and gives this kind of phenomena like interference and diffraction, but that didn't stand. On the contrary, this theory, wave theory, which was given by Fresnel, given by Huygens and finally modified by Fresnel, would explain the interference and diffraction and relating it to the wavelength of the light. So ideally we say that if the size of the obstacle is A and the wavelength lambda, so if lambda is very, very, A is very, very large as compared to lambda, or lambda is very, very small, lambda tends to 0 as compared to this, or the ratio tends to infinity, it's a perfect fit that you consider that light to travel in straight line. But if it is not so, then you will have this interference diffraction of light. Up to this, it was fine, but people are not very sure about the nature of this wave, light waves, because you know that there are two kinds of wave. One is your longitudinal wave, another is transverse wave. And sound travels as a longitudinal wave, right? Compressions and rarefactions. But light travels, light is basically a transverse wave, which was proved by another phenomenon which was exhibited by light, is polarization. So polarization of light confirmed that light is a transverse wave. Then finally, Maxwell gave a theory. Maxwell said that light is nothing but any other electromagnetic wave. Only the thing is that the frequency of light is very high. So in the tune of 10 to the power 14 hertz, right? A typical microwave signal will be of the order of say 10 to the power 9 hertz, which is 1 gigahertz, right? And you know that there are different ranges of frequencies, right? High frequency, ultra high frequency, very high frequency, ultra high frequency, microwave, millimeter wave. So there are different wavelength bands or frequency bands which are given different names, right? So generally microwave, we say that it's of the order of gigahertz, and you say that it is 10 to the power 5 times more. And Maxwell said that like any other radio waves, electromagnetic wave, where you have the E vectors and the magnetic field vectors, they are perpendicular to the direction of the propagation, direction in which the wave traverses. So he said that light should be viewed as an electromagnetic wave. So, and all these phenomena which light exhibited could be explained with the help of the existing theory of light, right? So depending on the situation you apply, we can, it becomes very easy to visualize when you consider rectilinear propagation of light. because you can trace the path of light for explaining a lot of simple bulk phenomena of light, right? And you can explain the same reflection with wave theory, but that becomes little cumbersome than considering it linear concept. And Maxwell's equation is more generalized, as you know that when you study the propagation of electromagnetic waves to a waveguide, you can write Maxwell's equation with the boundary conditions of it. Exactly in a similar way, when light travels through a kind of waveguide, right? That may be a planar waveguide or an optical fiber. You can write down Maxwell's equation and solve the Maxwell's equation to get the electric field, magnetic field, the power which is flowing through that. So all these calculations you can do with the help of Maxwell. But the problem came when this black body radiation explanation was needed, then how to explain the black body radiation, and the classical physics, the theory that could not explain the your electromagnetic radiation from black body. So Planck put forward the idea that the quantum theory, he said that this black body emits actually energy packets, quantum, and he gave an explanation to this black body radiation theory. Later on, Einstein explained photoelectric effect. Scientists observe this photoelectric effect, but there's no explanation of this photoelectric effect. Photoelectric effect is, in a simple way, you can understand that there are certain materials which are called photosensitive materials, because all materials may not show this property. When light strikes this material, then electrons are ejected from the materials. Electrons come out from this material. There are certain conditions which this light has to satisfy so that the electrons come out from this. So this is something which cannot be explained by the previous theories which are proposed for light. So Einstein used this concept of this black body radiation, the theory which was put forward by Max Planck. He used this theory, and which believes that this light is in the form of, this electromagnetic wave is in the form of energy packets of quanta, right? And each carrying an energy, tiny particles, right? Which carry an energy of h nu, where h is Planck's constant, and nu is the frequency of light. And nu lambda is equal to velocity of light, c. And he explained that this photon, which carries energy of h nu, strikes an electron and transfers its energy to the electron, which gains energy, and finally it moves out of the material. So here you find that the interaction when we are considering with matter, according to Einstein gave a theory of this explanation of photoelectric effect by considering light as quanta, a stream of photons, right, which interact with the matter, transfer the energy to the particle in the form of electrons. Electron gain the energy and moves out of this material. So interaction of light with matter, we should consider the quantum nature of light. This is called quantum nature of light. So starting from in theory of light, you see that you find that so many different forms are simultaneously coexisting in this explanation of different phenomena which are exhibited by light. Right, but since in optoelectronic devices you find that since the interaction, because devices or materials when it comes, so it's matter. So when this interaction comes with this matter, then we'll consider the quantum in nature of light, where we'll be considering light as stream of photons, right? And each photon carrying an energy equal to h nu, right? And so nu and lambda, either we talk in terms of nu or we can talk in terms of lambda, but you'll find that in optoelectronic devices, we more frequently we talk in terms of lambda. Even in optical communication also you'll find that even though in almost all electrical communication we talk of frequency bands in which we operate, but in optoelectronic you'll find that we talk about the wavelength, right? Say today's latest generation optical communication is at 1.55 micron, which is the wavelength. Because this is the wavelength that which optical fibers give you the least your attenuation at 1.55 micron. So that is the target wavelength, and entire communication system is based on that. So it's very common to talk in terms of wavelength rather than frequency. In all of electronic devices, you will see that when it's optical source, we will characterize the source in terms of wavelength rather than in terms of frequency. So this is the light aspect part of this, which will be involved in this. But nevertheless, there will be situations when we will be considering that propagation of light through a planar waveguide, right? Which can be developed on a semiconductor substrate, this planar waveguide. And when the light travels through that waveguide, then you can consider light in the form of your Maxwell's electromagnetic wave and write down Maxwell's equation and apply the boundary conditions to get the solution and how the light propagates through the waveguide. So that is one. But otherwise, all optoelectronic devices, this quantum nature of light will be taken into consideration. Now we come to the basic and fundamentals of your semiconductor devices, which knowledge will be required. So we go to the next page. So in today's lecture, I'll be focusing primarily on two basic optoelectronic devices. One is optical emitters, also called optical sources. We'll talk about optical detectors, which are called photodetectors also. Third, I'll talk about your photocell. Most popular member of the family is solar cell. Little bit. Why actually there are many optoelectronic devices, large number of optoelectronic devices, across optoelectronic devices. But these are very fundamental optoelectronic devices. And you will be surprised to know that all these three basic devices, they work on a simple electronic device, which is a PN junction diode. Right? How a PN junction diode can be used as an optical emitter, and how it can be used as an optical detector, and how it can be used as a photocell or a solar cell. I'll tell you. And to understand and appreciate that, you need to know a little bit about this. I know some of you know this basic fundamentals of semiconductor devices, but I was given to understand that there are some students who are in the second year also may not be very thorough. Just to brush up, I'll just tell you that, and many things which may not be covered in your traditional course on electronic devices, I'll tell you about those, because these are very important to understand these optoelectronic devices. Basic physical phenomena which are involved, mechanisms which are involved rather, this is very, very important. Sometimes you study from books and routinely you mug up certain things, you do not understand the things probably. So I'll try to make it clear as possible. So let us start with a very fundamentals. You know that when it comes to studying the semiconductor devices, quantum mechanics play a very important role, right? And many of these basic derivations are done from quantum mechanics. So I'll not get into that quantum mechanics because that will will not be possible within this 2 hours. So I'll assume that you know that what a semiconductor is. As you know that these materials, if you characterize this from electrical point of view, there are many ways of characterizing the materials. But when from the electrical point of view, we can primarily divide them into 3 categories. One we call your conductor. Second is insulator. Third is semiconductor. So this from the electrical point of view, this conductivity is obviously the electrical conductivity we are talking about. And you know that energy band diagram or energy band diagram or the structure, band structure of material, this is very, very important. Again, it's a very vast topic, but I'll just make it very easy. If you start from Bohr's theory, when you find that an isolated atom, you find that there is a nucleus and electrons are orbiting across along this nucleus in circular path. And Bohr gave a theory that when the electron gets excited, they go to higher excited orbits, and when they jump down from higher excited orbit to lower orbits, they release the energy, right? Which sometimes you see in the form of light, right? And in hydrogen atom, you see that the basic fundamental hydrogen atom, you find large number of spectral series which come like Lyman series, Balmer series, Paschen series, which you have studied in physics, that electron going to higher orbits, jumping to lower orbits, release some spectral lines. So this is the simple theory of hydrogen atoms. But when in a matter, or in a solid, large number of atoms are put together, right? When large number of atoms are put together, so the behavior of this solid will be different from the behavior of an individual atom. This is very, very important. And that is why we see that when we talk of nanotechnology, we say that why this nanotechnology is so important. It's not that the size of the devices is very small. What is very interesting is that these materials show certain properties which a bulk solid material doesn't show. Same solid material. So for example, if you have silicon, solid bulk material of silicon and silicon substrate, and this silicon in the nano form, nanosilicon, we'll find that there is a huge difference in the properties which are exhibited by a bulk material and this nano material. Reason is that the kind of bonding this silicon is having in the solid is different from the kind of bonding it is having in this nanomaterials, and that is reflected or manifested in the form of a difference in the properties which are exhibited by the same material in the different form. Right. So when they come into the solid, then you find that there is certain distance, that interatomic distance of spacing, where they finally these atoms settle for. And if you think in terms of your quantum mechanics, because you know that for dealing with atoms or subatomic particles, you need to take help of quantum mechanics, because your classical mechanics will not hold there. Classical mechanics, in the sense your Newtonian or Hamiltonian mechanics, will not work there. So in subatomic particles, you have to believe that there is some wave which is associated with the particle. Something similar to what de Broglie predicted, that matter is associated with waves, and he said that the wavelength can be calculated as lambda is equal to your h Planck's constant by momentum. He gave the formula, but later on in quantum mechanics, which was formulated separately by Heisenberg and Schrödinger, and in semiconductor device analysis, we mostly focus on Schrödinger quantum mechanics form, which is called wave mechanics. And the other one is matrix mechanics, which was developed by Heisenberg. They are basically the same thing, but in different forms. So wave mechanics, when we apply, you find that all these solid, when these atoms come closer to each other, then these subatomic particles, electrons, and their wave function associated with this, they interfere, and they form a kind of band structure for that solid. And when you study a large number of such solids, from electrical point of view, you can classify them under your conductor, insulator, and semiconductors. So these materials, we find that there are certain materials. More than that, I cannot discuss here how these bands are formed. So we believe that finally they form two bands, right? And one we call the conduction band, and the other one we call the valence band. And the separation between this conduction band and valence band, they differ from a solid to another solid, right? In some solids, you find that this distance, which is called the forbidden gap, energy gap, Eg, is very large. Some materials, it is moderate. And in some solid, you find that you cannot distinguish any difference or any gap between this conduction band and valence band. What these bands basically are, they are actually energy states, allowed energy states. According to quantum mechanics, you will find that the basic difference in classical mechanics and quantum mechanics. Classical mechanics, given some initial condition, you can precisely calculate the future things based on certain initial condition, because they will follow some formula. You put it in the formula. But according to your classical mechanics, probably you say that it is not possible to precisely tell the position of a particle, right? What we can calculate probably is the expectation of finding a particle, right? And according to Bohr's theory, you see that the energy orbits, they are discrete in nature. And he said that the energy is discrete. And here also, if you try to find the band structure of a solid using quantum mechanics, you'll find that there are certain allowed states which the particle can occupy. So for example, if we talk about electrons, so there will be some states which are allowed states, and between these allowed states, there is no other allowed state. So if there are two energy states, E1 and E2, it can go either to E1 or to E2, but there is no energy state in between. They are discrete in nature, not like your continuous things, right? So these are allowed energy states where the electron can go and stay, right? So in the valence band, and so these are the lower energy states and these are the higher energy state. They are clubbed together in the form of band. So if the energy band gap, and there is no allowed state. So if an electron has to move from valence band to the conduction band, so there is no other energy state, so you can go to the conduction band. There's no other place here. So if this forbidden gap means there is no allowed states in between these two, is greater than, say, 5 electron volt, then we say that this is an insulator. And if it is typically Eg is between 1 to 2 electron volt, we call it a semiconductor. And in conductors, these two virtually overlaps. There's nothing like conduction band and valence band separately. So it is, metal is seen as your sea of electrons rather, where ions are embedded into the sea of electrons. And these electrons, according to quantum theory, no longer belong to any particular atom. They are all contributed. And so whenever you apply a little voltage across this, the current starts going to the conductor. But this doesn't happen in the case of insulator and semiconductor, right? So you have the valence band, most of the states you find that they are filled up and the states are empty almost in the conduction band. So if you move an electron from valence band to the conduction band, they have a lot of energy states available through which they can propagate. or move very easily, and conduction can take place. And since it is a little cumbersome to draw all these lines again and again, these bands again and again, we represent this by two lines, right? One representing the bottom of the conduction band. We write conduction band, but we show a line. What is the implication is that there are allowed energy states above this. There are allowed energy state below this. So this valence band, when we draw a line, we are actually implicating that this is the top of the valence band, top of this, and this is the bottom of the conduction band. So this is these two lines representing the bottom of the conduction band and the top of the valence band is very, very useful in describing the transport of charge carriers, in particular in semiconductors, right? So this kind of diagrams will be called image band diagram. Now, as I said, that different solids exhibit different properties. Let's say metal, if you take say gold, silver, etc., the conductivity, electrical conductivity will be very, very high, and for insulator, it will be conductivity will be very, very low, and for semiconductor, the conductivity will be in between. And as I said, that the energy band gap will be 1 to 2 electron volt. What is electron volt? Electron volt is the amount of energy which an electron gains, right, when it is accelerated across a potential difference of 1 volt. So it becomes 1 volt into the charge of electron Q, which is 1.6 into 10 to the power minus 19 coulomb into 1 volt. So this becomes 1.6 into 10 to the power minus 19 joules. Right? So this is 1 electron volt is equal to. So it is very convenient in place of writing something minus to the power minus joules. It is very convenient to write in terms of electron volt. And if you remove this E, it is actually the potential. If we say 2 electron volt means that as if the electron is energized across a potential difference of 2 volts. So volt and this energy conversion becomes very easy. So we'll talk in terms of electron volts. Right? Now I start telling you that initially the electronics business all started with your vacuum tubes, where a cathode used to be heated and electrons are emitted from the cathode, which is subsequently collected by anode. Right. Now later on in during Second World War, people started working on these semiconductor crystals materials, and these crystals actually transform the entire world today, as you see today. So these are semiconductor crystals. So initially, the first starting point, if you see the field of semiconductor devices, was the invention of a bipolar junction transistor, right? And you may be knowing the history of this invention of transistor, which was done by 3 researchers working, scientists working in your Bell Lab. They were Bardeen, Brattain, and Shockley. So they invented transistor. You may wonder that why I came to transistor before telling you about PN junction, right? PN junction was invented rather little accidentally. Accidentally in the sense that when the researchers were trying to see that effect of light on matter, accidentally this PN junction was detected that the semiconductor material exhibits different property in different regions, right? And how this PN junction was discovered that way initially Later on, this was used by Shockley for explaining the operation of a transistor. Before coming to this p-n junction and transistor, I do not know all of you remember or recall what this p and n is all about. So let me talk a little bit about the semiconductors before I come to the junctions. Because this was historically important, that's why I just mentioned that the transistor was invented, and p-n junction was not an invention as a device, rather it was an outcome of some other study which was later used for explanation of this mechanism of operation of a bipolar junction transistor, which was invented by Shockley, and Bardeen and Bratton. They invented transistor in a different form, was a point contact transistor. Okay, so let us see as the semiconductor materials. If you see, I told you that semiconductor crystal, these are all crystalline materials. As you know that these solids can be again divided into categories like crystalline material or single crystal material, polycrystalline material, or an amorphous material. Right. So most of the semiconductor devices uses single crystals. Even though you'll find that there will be use of amorphous material, there will be use of polycrystalline materials also in many applications. Polycrystalline silicon, for example, we'll be using amorphous silicon also. So crystal structure again is another subject. So I do not know. Probably you may be feeling some jerk. I am coming to some points and going back to some, because you need to know, since we are talking of crystalline material, what are the different kinds of crystals and semiconductor crystals. Those are available, and how to analyze all these things. And the energy band structure, which I've shown you by two lines, is a very rudimentary form of energy band. Actual energy band structure in solid is much more complex than this, and that will only come when you use this quantum mechanics to analyze this energy band. Right. So semiconductors are basically, if somebody asks, the conductivity is in between insulator and your insulators and conductors, right? And or in terms of energy, band gap, forbidden gap, you say typically 1 to 2 electron volt. But you have semiconductors like indium antimonide, which has a band gap of the order of as low as 0.2 electron volt, and zinc sulfide, which has a band gap of 3.6 electron volt. So generally we say that 1 to 2 electron volt says that it is a semiconductor, right? Now, if you see the periodic table, you will find that we have two elements in the periodic table, and that is in group 4, which are semiconductor, which exhibit this kind of band diagram which I have told you. They are silicon and germanium. So these two semiconductors are called elemental semiconductors. Because they are elements and they belong to periodic table. Both of them belong to group 4. Silicon has an atomic number of 14. 1s2, 2s2, 2p6, 3s2, 3p2. So in 3s and 3p you have 2 electrons. So it has 4 electrons in the outermost orbit, right? And that makes it valence 4 of silicon, and this silicon forms covalent bond with adjacent silicon atoms. Right? In semiconductors, when it forms a solid or a crystalline structure, right? There are different types of bonding which occur, right? One of them is your ionic bond, as you know, in a crystalline sodium chloride, NaCl, you have ionic bond, right? But solids like silicon and germanium, they form covalent bond by sharing their outermost electron. Both has electron in the outermost orbit, 4 electrons. So, and 8 electrons in the outermost orbit will give you a stable structure. And both silicon and germanium share electrons with the adjacent 4 silicon atoms or 4 germanium atoms and form a covalent bond. And it gives you a interpenetrating face-centered cubic structure, FCC structure. Simplest structure is the cubic structure, where you have atoms in all corners, right? And when you have atoms in the face, each face also, that becomes a face-centered cubic structure. And this is little more complicated than the simple face-centered cubic. It is interpenetrating face-centered cubic structure, which is generally called as diamond structure. Both silicon and germanium has a diamond structure, right? So if you see a silicon, so a central silicon atom will have 4 electrons in the outermost orbit, which will share electron with 4 adjacent silicon atoms. And form a complete covalent bond with 8 electrons in the outermost orbit. Each of these silicon, this will also share with 4 like this, and they form a crystalline structure, which is an interpenetrating face-centered cubic structure or a diamond structure. So these two are the semiconductors. So for example, silicon has a band gap of 1.1 electron volt, right? And germanium has 0.6 electron volt around. Again, electron volt, this band gap will depend on the temperature. So normally our temperature which we talk about is 300 Kelvin temperature. Okay, so this is one class of semiconductor which are called elemental semiconductor. But there are other semiconductors which are compound semiconductors. These compound semiconductors are very, very important for optoelectronic devices. So there are many forms of this. Say we can have an element from group 3, an element from group 5. So these are called 3,5 compounds. We can have 2,6 compound. So we can have large number of semiconductors by combining elements from different groups, right? And we can have some alloy semiconductor like 4,4 compound. They are rather alloy, 4,4 alloy. Like you can combine germanium and silicon. Or you can have compound like silicon carbide. So this is another example of semiconductor. And if we come to these compound semiconductors, you'll find that say 3,5, let us say for example, if I take 3,5 semiconductors, gallium is a material which belongs to group 3, arsenic is a material which belongs to group 5, and this forms a compound gallium arsenide which has a band gap of 1.43 electron volt, 43 electron volt. So this is a semiconductor. Like you can have aluminium from group 3, arsenic from group 5, and it makes aluminium arsenide as a band gap of 2.16 electron volt. It's another semiconductor, right? You can have indium from this group and phosphorus from this group. You get indium phosphide, which has got band gap of 1.35 electron volt, right? So likewise, you can have a long list of materials by combining different elements from group 3 and group 5 to get different semiconductors, which will have a band gap of 0.2 electron volt. Okay, so these semiconductors, compounds which are formed by taking elements from group 3 and group 5 are called compound semiconductor. Since 2 elements are involved, they are called binary 3,5 semiconductor. right? Likewise, you can have 2,6 materials also. Right? Say CDT is a semiconductor, cadmium telluride is a semiconductor, group 2 and group 4, 6, that makes another semiconductor. The group 2 elements means 2 electrons in the outermost orbit, 6 electrons in the outermost orbit, right? 6 plus 2, that makes it 8 electrons in the outermost orbit, right? Here you have 3 electrons in the outermost orbit for gallium, arsenic, you have 5 electrons. So it forms 8 electrons in the outermost orbit. Band gap is increased, so they are semiconductors, right? But what will be the crystal structure of this semiconductor? This crystal structure will be little different from diamond structure because you have the electrons in silicon, all atoms were silicon atoms, or in germanium, all atoms were germanium atoms, and all of them were donating 1 electron to the adjacent atom to complete their covalent bond, right? So this was purely a covalent bond, but in the case of 3,5 material, it is partially ionic and partially covalent. Covalent. It is not a pure covalent bond, but they behave as semiconductor, and this kind of crystal structure, which is again face-centered cubic structure, interpenetrating face-centered cubic structure, but they are similar to zinc blende structure, ZNS structure, right? Interpenetrating. Face-centered cubic structure, zinc blende. One is zinc blende structure, another is diamond. Basically, they are same. The only difference is that in diamond structure, all atoms are carbon atoms. And here you have the mixed atoms of gallium arsenide or arsenic or aluminium or arsenic like this. So these materials are very, very important for optoelectronic devices. These 3,5 materials or these 2,6 materials for making a lot of optoelectronic devices which you cannot use silicon, right? So that is one important thing. And second important thing which you'll find here is that you can design a lot of materials using this concept of mixing, right? There is a time when semiconductor devices, the engineers who were working with semiconductor devices, the device engineers had a limitation in terms of the available material. Why? Because ultimately the properties or the outcome which you want from the device is restricted by the properties of the material, right? So if you have a restriction on the properties of the material, then you cannot use it in the proper way to have multiple functions for a single device. But today the technology has advanced so much that you can design a material, you can tailor the property of the material, and that is a huge flexibility for making devices. Now I can have a material which can exhibit a lot of properties apart from semiconductor properties. Say it will exhibit magnetic properties, it will exhibit piezoelectric property, right? It will exhibit optical properties. So this way I can have a device where all these properties can be utilized to make different kinds of devices using the same materials. So this is a huge kind of flexibility now we are having. So it's not that compound semiconductors have come in the recent years. Compound semiconductors were studied long back, particularly for infrared detection, etc. People were using. But now there's a systematic study, and in the lab you can develop this material and you can tailor the properties of the material by adding small impurities to the material, right? So this is one example I'll give you. Say for example, I take gallium arsenide for example. Now in this material, if I add another group 3 material, right? Then say I want to add aluminium in gallium arsenide. So if I do it, then the aluminium atoms will replace gallium atoms from the gallium sites, and occupy those positions. So some places it will be aluminum, some places it will be gallium, and some places it will be arsenic. And you get a new material which is aluminum, gallium, arsenide. So, arsenide. Right? Now, suppose if I add 30% aluminum to gallium arsenide, then 70% of gallium will be left, 30% of gallium will be replaced by aluminum, and arsenic will remain unaltered because group 3 is not going to replace group 5. So, if I so these are characterized by a parameter called mole fraction x. If it is x, then it will be 1 minus x. X is mole fraction. So if I have added 30% of aluminum, then it becomes aluminum 0.3, gallium 0.7, arsenic is a material. So I got a new material. Right? Now, this material, now if I change this aluminum, this composition to 0.33, gallium 0.67, arsenic, it becomes another new material. The property of these two materials will be different. What are these properties? Its band gap will be different. Its lattice constant will be different. Right? Its mobility will be different. Everything will be different for these two materials. Right? So the electrical properties, the optical properties of these materials will change. Now I can tell the property by changing the composition of the material. This is a huge flexibility. You understand that? So I can create a lot of materials, like say, if I take gallium arsenide and add phosphorus to it, I can get a new material which is called gallium arsenide phosphide. So it will be gallium, arsenide is group 5, so phosphorus will replace a group 5. So it will be 1 minus x, phosphorus x. Now I change the value of x. X can be changed from 0 to 1. If I make x 0, then it will be gallium arsenide. If I make x 1, it will be gallium phosphide. In between, it will be a material which is called gallium arsenide phosphide. Right? Now I can play with this x value and change all the properties of the material. So I can design a material so that what I expect from the device can be achieved. So this is a huge flexibility we are having today. Okay, so this is compound semiconductor. So since it involves 3 elements, so it is called a ternary 3-5 semiconductor. Same thing can be done in the case of 2-6 also. So for example, HgCdTe can make. So HgCdTe will be a material which is a ternary 2-6 material. It is called mercury cadmium telluride MCT material, which is used in low wavelength detection, optical detection, in longer wavelength. Longer wavelength detection, IR detection. LWIR, you can say long wavelength infrared detector. This material is used. So these materials are ternary semiconductors. So here it is ternary 3-5 semiconductor. Exactly in a similar way, I can change simultaneously both group 3 and group 5. If we do that, then you get another class of materials, like say, I have gallium arsenide and I add indium here, phosphorus here. So indium belongs to group 3, so indium will replace gallium. Phosphorus will replace arsenic. So we have 2 mole fraction, X and Y. So this gives a new material which is called indium, gallium, arsenide, phosphide. So this is called a quaternary compound. Sometimes they are called alloy semiconductor also. all these semiconductors, they are not stoichiometric compounds. You find that the fraction, they do not have this simple ratio of simple numbers, right? So some book you'll find they are calling it other semiconductor. Some people call it compound semiconductor. Some text you'll find only 3-5 semiconductors, 2-6 semiconductors, like this, right? So you can have a host of semiconductors, quaternary semiconductor, by combining different elements and making a semiconductor. Now the properties can be changed. Let us come to one property, say, for example, the band gap of the material. If you say, how we can tell us. So this will give you an example that how this property can be changed, right? So if we take, for example, band gap of the material, right? Say I will take the example of aluminium, gallium, arsenide. So we say it is aluminium X, gallium 1 minus X, arsenide, right? And I plot the value of the band gap of the material, because band gap of the material will be different from gallium arsenide. It will be different from aluminium arsenide, but it will have a value in between gallium arsenide and aluminium arsenide, right? So this is X is equal to 0. This is X is equal to 1. Okay. So when X is equal to 0, then it becomes gallium arsenide. And when it is X is equal to 1, it is aluminium arsenide. So its band gap here is 1.43 electron volt, and its band gap is 2.16 electron volt. Now when I change the value of X, my material is aluminium X, gallium 1 minus X, arsenic, right? So as you change the value of X, you'll find that the band gap of this resultant material changes in some fashion, right? That can be measured experimentally, not generally a linear manner, but generally it is a non-linear fashion. It varies. It varies from 1.43 to 1.46. Say if you say my X value is 0.3, then I can find out what is the corresponding band gap from this part, right? So this is the corresponding band gap of this material. Okay. Now alternatively, if I want a band gap of 1.8, I can find out that what should be my value of X so that I can design the material. So from this, I'll go here, locate the point, find the X value here, whatever X value we get here, I can design that material. This will be aluminium, this, gallium 1 minus this, arsenic will be the material. If this comes out to be 0.4, so I'll say this 0.4, this is 0.6, arsenic. So that is the material. I give you an example of the optoelectronic device, or simply it's not device, we are still considering a material. What could be the application of this material? For this, we need to understand that there is a relationship in optoelectronic device. It is very, very important. There is a relationship between the band gap of the material and the wavelength of the light which interacts with that matter. Right? There will be certain wavelength for which the material will work as a transparent material. Whether a material is transparent or opaque to certain substance depends on the wavelength of that, or the frequency of the light, or we can say the photon energy. Like whether it will behave as a window, like light will come and pass through it without doing anything, right? So we'll treat it as a transparent material, right? If we change the material, that same light may be, that material may be opaque to that same light. but other materials may be transparent. So whether it is transparent or opaque will depend on the value of this wavelength, right, or the nature of the substance. Okay. Now in a semiconductor, when we describe with a simple picture like this, which you'll find that in optoelectronic device, you'll find difficulty in explaining certain properties by using this simple energy band diagram, where we call it the conduction band and this we call it the valence band. So at absolute zero in a semiconductor, all the states in the valence band are filled up, and all the states in the conduction band, they are empty. There are a large number of empty available states in the conduction band, and all states in the valence band are filled up. Right. So a semiconductor at absolute zero degree Kelvin, it behaves as an insulator. Why insulator? Because there is no electron in the conduction band. So if you apply an electric field, nothing will happen because all states are filled. So the electrons cannot move here. There's no electron in the conduction band. So at absolute zero, it will not exhibit any conductivity. So it will be an insulator. No current will flow through this semiconductor, right? But when you take this to a certain temperature, say room temperature 300 Kelvin, we'll find that some of the electrons will gain energy from this and they will move to the conduction band. Right. Once they reach the conduction band, they find lot of allowed states. Allowed states are required for the energy to move when you apply an electric field to it. Right. So you find that good number of electrons will come into the conduction band. So this will have some electrons, vacancy of electrons, which we call as holes, and some electrons we find in the conduction band. And when this creation of electron is there, each electron which is moving from valence band to the conduction band is leaving a vacant position, which is termed as hole. Concept of hole is little complicated. If you do not take help of quantum mechanics, you will not be able to understand. But for a macroscopic description in semiconductor device analysis, we normally do a macroscopic analysis. Macroscopic analysis means we do not apply quantum mechanics or go to subatomic level and we try to investigate what is happening. For the electronics engineers, it is important that we analyze it by the terminal behaviors, like we apply a voltage across this device and how much current is flowing. This kind of description is a macroscopic description. In a macroscopic description, the holes are treated as positive charge. There are ample evidence to prove that holes behave as positive charges and electrons behave as negative charge. This means that when you apply an electric field, the electrons will move in the direction opposite to the field to have the minimum energy, and holes will move in the direction of the electric field. So this is in a macroscopic description. But back in this band structure level, you'll find that something different is happening, that how these electrons are moving through different quantum states available to it, and how the holes are moving. Basically, electrons are occupying those positions, and that's how the conduction is taking place to the valence band. But in a macroscopic description, we simply treat them as positive charge, electron is negative charge, minus Q, and holes are carrying positive charge, and they are moving in the opposite direction. Okay. Now, these carriers, when they are generated because of thermal energy, they are generated in pairs. So these are called electron-hole pair. Because every electron which moves from the valence band to the conduction band leaves a vacant position back in the valence band, that is treated as a hole. So if 10 electron moves, there will be 10 vacant positions. So you will have 10 electron-hole pairs generated here. Right? So this kind of generation is called thermal generation. Why we need to understand? Because we will have an additional generation because of now light coming into picture. And here, this is purely electronic device where you are seeing that thermally generated carriers are there. Now I will apply electric field, and what is happening? I'll see in that. But in optoelectronic device, in addition to these thermally generated carriers, we'll have some additional carriers which are generated by light. Okay. But you know that in semiconductor, why the semiconductors are so important? Since you are interested in the electrical characteristics, obviously people will be interested in conductors. Why semiconductors? The biggest advantage of this semiconducting material is that you can change the conductivity of the material. That is the biggest advantage of, and that in a process gives you lot of functionalities which you can get from the material. And that's the advantage why we are interested, despite the fact that its conductivity is in between insulator and conductor. So we can modulate this transport of charge carriers to these semiconductors, or we can modulate the conductivity of these materials by external forces, either by applying a voltage, or we can shining a light, or different ways, or bombarding some high energy particles. I can change the conductivity of the material, and I can get lot of functionalities which this device does, and that's why we are interested in semiconductor devices. So let me go quickly, as I think you know. So that I told you that semiconductors materials will be one is elemental semiconductor, and another is compound semiconductors. But all the semiconductors basically inorganic semiconductors. But later on, it was found that some of the organic materials, they also exhibit semiconducting property. So in 2000, it was established that there are certain organic crystals, like small size crystal, large size crystal, and organic polymers also, they exhibit semiconducting properties, right? And you must be aware of optical organic LEDs, light emitting diodes, which are being used, and maybe you are using your smartphone, which involves your organic light emitting diodes. You have televisions which are made by Samsung company, as well as your LG companies who are using optical LEDs based television. So these are going to have a huge share of market. 30 to 40% of display market will be by organic materials. So organic semiconductor is, just for your information, organic semiconductors are also coming in a big way as semiconducting materials, and they are being used. It has a lot of advantages. One of the major advantages is that the devices which are made out of this are flexible in nature, are stretchable. Means that tomorrow you can have a mobile which you can fold like a piece of paper and put it in your pocket. So that kind of technology it is going to be. So organic semiconductors are also coming in a big way, and optoelectronics particularly, these organic materials have got huge applications. Why OLEDs are so important? Because they can give you some color which is really unmatched, which are very close to realistic color, which cannot be obtained by inorganic materials. These organic semiconductors are a lot of drawbacks. I have not come into that, just for information. So you have inorganic materials, organic materials, you have semiconductors which are elemental semiconductors, you have compound semiconductors or alloy semiconductors, and on the top of that you have organic semiconductors. Now you can make semiconductor devices making a combination of organic and inorganic materials. Those are hybrid devices. Hybrid junctions you use, which make use of organic semiconductors, inorganic semiconductors, in an attempt to make use of best of both the worlds. That what are the advantages of organic materials you get, that you pull in, and what are the advantages of inorganic material you take in, and then you get a device which can outperform the existing device. But it's not that easy, it's not that rosy. There are a lot of hurdles in the process which are there. But it's just for your information. So we are not coming into the discussion of organic semiconductors. Okay, so let us move back to this our discussion. And in the semiconductor, you know that, as I told you, that conductivity of the semiconductor is can be modulated, can be changed. One of the ways of doing it is by doping. As you know that we can dope a semiconductor, and we can change the conductivity of a semiconductor, right? And doping is one of the mechanisms, and there are certain impurities. A semiconductor in the purest form is an intrinsic semiconductor. Intrinsic semiconductor. Intrinsic semiconductor means it is 100% pure semiconductor, which is not possible. Right? None of the materials can be obtained as 100% pure. There will be some impurity so intrinsic semiconductor is something which is idealistic. Means there is no impurity in the semiconductor, means you will have a conduction band which can be shown like this, valence band, and you can have a conduction band, we will have this, and this entire region is completely forbidden. There is no allowed energy state. If there is an impurity, this may give an energy state in the forbidden gap, which will correspond to the energy level of that particular impurity. Right. Now, these semiconductor materials, it is possible to put some impurity, deliberately we call it. There is one impurity which can come because of imperfect manufacturing of the material. Some material is coming, say iron is coming, or aluminium, some material is coming because of some imperfection in your manufacturing process. That can give you an energy state in between. Otherwise, a pure semiconductor is one line conduction band, energy states above, valence band, energy states below. Rest of the region is forbidden. So, only way the electron holes can be created here is by thermal mechanism is one. That electron, if you give thermal energy, it will move, but their electron hole, they will be in pairs. So there will be as many electrons will be there, so many holes will be there also. Right. So we say that the concentration of electrons, which is denoted by N, and concentration of holes in the semiconductor will be the same. So an intrinsic material is one in which the number of electrons is equal to number of holes. All these number of electrons and holes are measured per unit volume. In MKS unit, we denote it by per meter cube. Right? And in silicon, say for example, this is concentration is 1.5 into 10 to the power 16 per meter cube. This is the number of electrons and holes which we find generally in silicon at room temperature, because it is temperature dependent. Okay, but if we add some impurity, small amount of impurity in the semiconductors, right, we can change the number of electrons or number of holes in the semiconductor by choosing the impurity properly. Say for example, if you choose in silicon, if you choose an impurity from group 5, then you can create large number of electrons in the semiconductor as compared to holes. And this semiconductor, since large number of electrons, originally the name was coined from the fact that it becomes negative kind of thing. But there's nothing like negative positive in semiconductor, because all the semiconductors are electrically neutral. Because you add impurity atoms, not ions. So when you add atoms, the total thing remains electrically neutral. So it becomes N-type, and the other becomes P-type if you add group 3 element. This can be understood very easily, because if you put a phosphorus which is pentavalent, these are 5 electrons in the outermost, so it will replace the silicon and share 4 of its outermost electron with 4 adjacent silicon, and 1 electron will be loosely bound to phosphorus, which with a little amount of energy can be released, and it will go to conduction band. And that's how you have large number of phosphorus atoms. They will donate their electrons, they will go to conduction band. And likewise, if you add a group 3, it will not be able to complete the covalent bond, because it has 3 electrons in the outermost orbit, so 1 electron will fall short, so it will create a hole. That's how you can create the hole concentration more in this type of semiconductor as compared to electron concentration. So they become p-type, holes are more than electrons, but nevertheless they remain electrically neutral. That should be remembered. So an n-type material, n is larger than p, right? Electron concentration is more than the hole concentration, and when you put group 5, so it creates an energy level This is the impurity level which will be within the forbidden gap. This is no longer forbidden. Now I have a physical energy level which is present here. This is the donor level which is corresponding to the energy level of the impurity. So this is donor level. And in the p-type semiconductor, this will give you an acceptor level. They are called shallow dopant because these are created very close to the band edges, right? Otherwise, if we choose another material that may give you an energy level somewhere in the middle, will not be effective for making it n-type or p-type. So it has to be a shallow dopant, which will give you an energy state very close to this. Okay. So this is all about n-type and p-type. Okay. So in a semiconductor now, you have thermally generated carrier, which are coming into this. And if you have a doped material, then in the conduction band, you have some electrons already present in the conduction band, and some holes will be there. And if you are considering an n-type material, then the number of electrons, normally we consider the concentration in equilibrium, so we call it N0 is the equilibrium concentration. Equilibrium concentration means there will be no net flow of currents now, carriers now. They are stable, and you have, and the semiconductor, there is no external voltage applied to the semiconductor. There is no light falling on the semiconductor. So if all these conditions are satisfied, then you will find an n-type semiconductor. N0 will be much larger than P0. Right? And when you put make these donor levels, right? So a typical doping could be of the order of 10 to the power 22 or 23 atoms per meter. Typically, it can be 10 to the power 24 or 10 to the power 20 also. Right? So if 10 to the power 22 is added, donors, so all these donors have extra electron which can get little energy and go to the conduction band. So we believe that at 300 Kelvin, which is a good amount of thermal energy to have, all these electrons will move to the conduction band. So whatever is the donor concentration, which is denoted by Nd, we can equate it approximately to the electron concentration. You may argue, sir, where is the thermally generated carriers which are coming? Thermally generated carriers number, I said that it is of the order of 10 to the power 16 per meter cube. So if this 10 to the power 16 is added to 10 to the power 22, it virtually remains 10 to the power 22. Right? So we say that now N0 is much larger than P0, so we have large concentration of electrons here. And the band gap of the material is, say, if it is silicon, it is 1.1 electron volt. Now, if we shine light on this material, right, of energy Hd, so this energy of the photon, an electron in the valence band can get this energy from the photon and can be excited into the conduction band. So many such electrons now can gain energy from the incoming light, which is in the form of photon, and can move to the conduction band. Right? So in addition to the thermally generated carriers which are contributed by these your donors, you will have additional carriers which are coming because of the generation of additional carriers by light. Okay, here also you see that whenever an electron in the valence band gain energy from the photon, they go to conduction band, you get one electron here and one hole is here. So here also you get one electron hole pair created by light. So the difference is that one is thermally generated carrier, which is already prevalent. So if the semiconductor is in the dark, there will be some carrier present in the conduction band, provided you are not at 0 degree Kelvin, right? If you are not at 0 Kelvin, so there will be some carriers which are present in because of this thermal generation. Now, if I shine light, then there will be some additional generation of carriers in the semiconductor, which will add up with the existing thermally generated carrier in the semiconductor. Okay, so this is interaction of light with the semiconductor causing it some change in the electrical characteristics, in the form of changed number of carriers in the semiconductor in presence of light. So this is the interaction of light with semiconductor. So what we expect to happen in the characteristics of this semiconducting material? Let us consider first before we come to junction. I do not know, I have exhausted almost 20 minutes left. Junction we have not left up. Anyway, so you will find that we have thermally generated carrier, then we have light generated carriers, which we call optically generated carrier. So photon falling on this, moving electron to this, which is adding up with the existing carrier here. Now you may question that any wavelength light will work. No, any wavelength of light will not work. There is a relationship that which you can appreciate, that energy of the photon has to be at least equal to Eg. If it is greater than Eg, it is fine. If it is equal to Eg, then it will move from the top of the valence band to the bottom of the conduction band. That is the lowest energy which is needed. If it is more, they will go higher up in the energy state, right? And because there are allowed states above, because there is no allowed state in between, excepting the donor level which has been created, and there can be a transition between the donor level and valence band also. I'm not coming into that, will make it more complex. So let us assume that the electrons have no other place than to go to the bottom of the conduction band, minimum energy needed. So we say that Hb should be greater than equal to Eg at the above the material. If we put the values of the physical constant, this finally boils down to the maximum value of lambda maximum, because lambda large means the wavelength is smaller, right? Lambda small means, frequency is smaller, and lambda small means frequency is higher. Okay, so maximum value of lambda will be 1.24 if you put the value of the physical constant, divided by band gap of the material in electron volt, this much micrometer. 1 micrometer is 10 to the power minus 6 meter. So this is the maximum value of wavelength. So if your wavelength and Eg is 1.1 electron volt, so you can find out for silicon what will be the wavelength of light that will be absorbed by the material. We say when this photon is transferring its energy to the electrons here, the photon is actually absorbed by the material. So I say that when this lambda is in this range, 1.24 divided by 1.1 electron volt, then in this range, then that light will be absorbed. So if you have a lambda light of wavelength which is very different from this which is coming from the calculation, it will not be absorbed by this material. Or either it will be absorbed very close to the surface, or it will be this material will be transferred to it. Now when this material, this wavelength of light falls on this material, extra carriers are generated, then it changes the electrical characteristics. Why I said that? Because the conductivity of the material, because both electrons and holes are moving in this semiconductor, electrons and holes are moving in opposite direction. So the conductivity of the material will be decided by the number of free electrons and holes present in the semiconductor. So when the semiconductor is in the dark condition, so some electron holes are present here. Now when you shine light on this material, then there will be additional electron holes which will be optically generated here. So because of larger number of carriers, the conductivity of this material will change. Right? So a semiconductor, if you apply a voltage across this semiconductor, some current will flow through the semiconductor, or if you connect a load across this, so some amount of current will flow through the semiconductor in absence of light. Right now, if you shine light, the conductivity of this or the resistance of this will change, and they will observe a change in the current, which will be manifested in the form of a changed voltage across this load. And you'll find that this can detect the presence of light, and this is called light dependent resistor. This is a resistance where this conductivity of this is dependent on light. And if the intensity of the light is changed, more carrier generation will be there. And you can find out from this LDR that not only the presence of light, but also you can find out that what is the intensity of the light. Because the number of carriers which are generated is directly related to the intensity of the light. So this is a very simple example where a bulk semiconductor material can be used to sense light. Right? So these are called photoconductors. But this can be made more effective when you make use of junctions. It's not that those who do electronic circuits and make a lot of sensors, these LDR sensors are available commercially available in the market. So if you want to develop a system where the lights can be automatically turned off depending on whether it is dusk or dawn, morning the lights will be switched off, and when it becomes evening the light will be turned on, can be used with the help of LDR sensor kind of things. But there are many sophisticated applications where you want these devices to work very fast, particularly for optical communication, etc., where you require a faster device. And these fast devices can be opted with the help of junction, right? So I don't know, because of another important thing which will be you need to know is about direct and indirect bandgap semiconductor, which is very, very important to know. Even though you will know that silicon is a material which rules the semiconductor industry, particularly for IC manufacturing, because silicon has the biggest advantage that you get an insulator on silicon by oxidizing it. That gives you a silicon oxide, which is an insulator. This is a natural insulator which you get in case of silicon. And since the MOS technology is used for making these ICs, silicon is the ruler of this semiconductor industry even today. But there is one area only where the semiconductor, the silicon could not compete with their counterparts in compound semiconductors like gallium arsenide and other material, is the fact that both silicon as well as germanium, even though less work is we are doing, silicon technology is more mature because of and several advantages of silicon. Germanium use as limited use. Both these materials are indirect bandgap materials. And a consequence of this becoming indirect material is that they cannot emit light. Can't emit light. Right. But on the other hand, you have gallium arsenide and a lot of other materials which are direct bandgap materials. Right? So direct and indirect bandgap materials can be understood by studying the band structure with the help of quantum mechanics, which results into EK diagram, where we say that we plot the energy with the momentum vector, right? And you get two class of EK diagram. In one, you find that this is the conduction band, this is the valence band, bottom of the conduction band is there, top of the valence band is this. This is the bandgap EG. This is one class of material. Another class, you get the valence band here, but conduction band minima is not occurring at the same value of K. K is nothing but We call it momentum vector. It is momentum scaled by certain factor. So we say that silicon and germanium exhibits a characteristics where the bottom of the conduction band and the top of the valence band, they do not occur at the same value of K. Now in a material, we say that when electrons and holes move from opposite direction, they collide and they vanish. The process is called recombination process. Now this recombination, one condition which is to be maintained, that the conservation of momentum. Momentum has to be conserved. And when you draw this diagram and you see that whenever an electron jumps from conduction band to valence band, this can occur without any change in the K value. But whenever this kind of transition needs to occur, then there is a change in K value. So that's how we classify them under two categories. One we call indirect, another we call direct band gap semiconductor, where the momentum is conserved. So here the momentum is cannot be conserved. So direct transition from conduction band to valence band is not possible. They generally occur through an intermediate energy level in two steps, and recombination is there. Now let us have a look at what this recombination means. So far we have seen that whether it is thermal generation or optical generation, the electron in the valence band get energy from the incoming photon, or thermal energy goes to the conduction band, creating electron hole pair. So it is creation of one electron hole pair. But the reverse thing also can. How long this electron which has been excited to the higher energy state will stay? Will it stay permanently? No. It has been excited, that's why it has moved here. So it will always look for an opportunity to come back to the lower energy state, right? But there is no other allowed energy state in between. So only way it can come back, it has to come back to the lower energy state, released in the valence band, right? Now, if it is successful in doing that, then it will have to release the energy, excess energy in some form. Now, if it is a direct band gap semiconductor, then you'll find that this energy is released in the form of photon or light, right? Whereas in indirect band gap semiconductor, where you have the conduction band here, this is released in the form of heat. So that heat which is released in the process is absorbed by lattice, which sets the lattice into vibration, and that lattice vibration is called phonon. So one is direct recombination, where the emitted light is in the form of a photon, right? Light is emitted, which is basically photon. So this recombination is accompanied by emission of photon. And this recombination is, the energy is released in the form of heat. So in indirect band gap semiconductor, you get heat which goes to lattice, but in direct band gap semiconductor, energy is released in the form of photon. So this material, when an electron jumps from valence band to the conduction band, we say it is recombination, and this recombination is accompanied by emission of a photon. So this material will be emitting light. It will be an emitter, right? It will emit light through recombination. Example, gallium arsenide is a material where it's a direct band gap material. So recombination will be the direct recombination and emission of light. But in the case of silicon or germanium or many other 3-5 materials also, all 3-5 materials or 2-6 materials are not direct. There are a lot of indirect materials also in 3-5. So there it will be in the form of photon. So these two characteristics which we have studied so far, one, we have seen that in one process, what we have called as generation, we see that light can be absorbed by the material, creating electron hole pair, which can change the electrical property of the material in the form of changing the conductivity, and which can be used for detection of light. So this is the generation process by light, optical generation. And the reverse process is recombination, where the excited electron comes back to the original band, releasing the energy in the form of photon, and this light can be, this material can be an emitter. It can emit light in a direct band gap semiconductor. So in a direct band gap semiconductor, you see that there is a possibility of emission. And how will you calculate the wavelength? The formula is same, because Eg is equal to hd. So what wavelength it will emit, that can be calculated by making Eg equal to hd. But you will find that none of this material will emit a single wavelength, right? But all these materials will have a band of wavelength, spectral width over which they will emit. So this will not be a monochromatic source, but it can emit, the semiconductor material can emit, and the emission is because of radiative recombination. This recombination is also called radiative recombination or direct recombination. And the detection will be possible because of optical generation done by this. Okay, so these are the two fundamental processes which are involved. Now we will see that we will not be using this bulk material for making an effective optical source or effective optical detector, but now we will be using junctions which can work more efficiently for getting these functions as a detector and an emitter. At this point of time, I like to interact. Do you want me to quickly tell you about this detectors, giving an example of PN junction, which I can do in 10 minutes by assuming that you have a fair amount of idea about junctions. Now, who is the instructor may advise me accordingly. Or even the students. You hear me? You hear me? Yeah, Professor Mannar. Yeah, Professor Mannar.
Yes. Sutapa, thank you very much, Professor Chakrabarti.
Sir,
And our HOD, I request our HOD Sutapa Chatterjee to come to the photo. Thanks for the Professor Chakrabarti.
Sir, sir, am I audible?
Yeah.
Sir, very many thanks to you, sir, for we have this enlightened lecture. So many details we have learned from this invited talk. Starting from the optoelectronics, photonics, and all the details of the devices we study in the optoelectronics devices.
Can I interrupt, please?
Actually,
I like to
actually from the
interrupt. Just let me tell you that probably I could speak about 30% of what I wanted to do, because in some portion I went in details, presuming that students may not be knowing those details, because the junction I could not discuss, because the material itself, and to know these fundamentals, I have to spend so much time. And if you want to have a real feeling of these devices, how they work, probably sometime I'll deliver another lecture on that how these optical devices really work. But this is very fundamental from the materials point of view, that what are the physical mechanisms those are involved in the operation of optoelectronic devices. I like to have the reaction from the students that if there are some queries. I'm not very much keen in these formalities of thanking me formally, because I'm more interested to have some reaction from the students.
Okay, sir.
Hello, good afternoon, sir.
Yeah.
Hello. Am I audible? Hello?
Students are advised to interact because Professor Chakrabarti has elaborately described about the semiconductor devices, how they are produced at various kinds of, what is their flexibility, what are the properties, from the very fundamental level, starting from the electronic configuration and the periodic table at the very fundamental level, and how the research has gone upward. And
Hello?
at the present
Good
stage.
afternoon, sir. Can I ask one
Yes.
question from my end?
Yes, please.
Firstly, I'm
Soma Sen, please.
yes, sir, faculty from Department of EC. So I've got two queries from my end. One is that, so you told about 3-5 semiconductors for the opto devices. So while simulating the devices, uh, the, how can we avoid the lattice mismatch? This is my query number one. And my second query is that, so while trying to simulate a nanotube to finally, I mean, any nanostructure to finally make any opto device such as laser or LED, so what are the preferable materials we can use to do so?
Okay, so you basically have two questions. You are asking about lattice matching.
Yes,
So how do you
that
correctly?
is mismatch.
Yeah,
How to avoid that?
lattice mismatch.
Yes.
How to avoid it?
Yes, sir. I mean the strained epitaxy or those strained lattice that comes by the simulation, the off current goes up. That is why I was asking about how to avoid that one.
Yeah, but for the students actually they will not be appreciating what this lattice matching all about. As you know that when I spoke about these 3-5 materials, my focus was mostly on the material itself rather than coming into any kind of junction. And the
Yes,
question suggests that when you form a contact between two different semiconductors, then the challenge of lattice matching comes. Right. Normally, a semiconductor, P-type semiconductor and N-type semiconductor, when you talk of a p-n junction, is not just a piece of P-type material and N-type material is connected. It is rather the same crystalline structure, and where we have created two regions with different conductivities, and that's an intimate contact, and that forms a p-n junction. So when the material is same, there is no problem, like which you call homojunction. Normal p-n junction, if the material is silicon and one side is P, other side is N, you do not encounter any problem. But all these 3-5 semiconductors which we use, they are mostly grown in an epitaxial fashion. Epitaxial manner, then you need a substrate on which these materials are to be grown. So for example, if you want to grow a gallium arsenide, aluminum gallium arsenide layer, then you have to grow with on a gallium arsenide substrate. The available substrate is gallium arsenide, to which it is lattice match. What does it mean? When you are using the same material, you never bother about this lattice dimension, which is called lattice constant of the material. The distance between these lattice points. So that distance is very, very important in any crystal structure. So when you have two dissimilar material, when it comes in heterojunctions, so there are two kinds of homojunction is same material you are using. When you're using two different materials, we call it a heterojunction. And when heterojunction is coming, then since you have two different materials, the crystalline structure will be different, their lattice constant will be different. Now, how you put one on the other? So when you try to put one on the other, then you have to take care of the fact that their lattice constants are nearly equal. So there are certain materials which are naturally lattice matched. So there's a very small difference in the lattice constant that doesn't create much of a trouble. But the trouble comes when these two materials lattice constant are very different. Then the question of lattice mismatch actually really comes. And there you have to, there's a strain layer, as you were saying, that there are many mechanisms by which this lattice matching is handled. First thing, the basic approach should be to select materials which are nearly lattice match, right? Otherwise, you'll have to take other indirect methods of handling this lattice mismatch in semiconductor, because the objective of making a heterojunction is to get some benefit in the outcome of this device performance ratings, and If you do not have a perfect match, then there will be a lot of interface states which will be created, and that will give you local surface currents, etc., and will spoil the ultimate performance of the device. Right. And in nanotechnology, what you have said, it is even more difficult, because when you grow certain materials, these are not at all lattice matched to this, and the crystal structure is also different. So this is the biggest challenge for the simulators. Those who are doing the simulation, it's really a big challenge. So for example, if you grow a layer of say an oxide semiconductor on silicon substrate, right, which gives you a heterojunction, and silicon structure, crystal structure, and say zinc oxide, if this is oxide semiconductor, crystal structures are also very different. So it's not only the question of lattice mismatch, but also the crystal structure is different. Something has hexagonal structure, one you have the FCC structure, and handling and modeling this theoretically is extremely difficult. And so normally that lattice matching factor, we do not, most of the analysis we do not consider, and basically we try to apply Anderson's model. Anderson's model is the fundamental model where you neglect the lattice mismatching or presence of interface traps there. So what you consider the idealistic situation, because sometimes based on your band gap of the material, what function, you decide whether it will form a type 1 or type 2 or a type 3 heterostructure. But when you really go to lab and make a heterostructure, you will find that this can be very different from what you have predicted theoretically. So and it is particularly in nanotechnology, it is largely process dependent also. And many of these semiconductors exhibit, depending on process, different kind of crystal structures also. And what is the growth direction, that also changes with the process. So all these normally we make an idealistic model in simulation. It's very difficult in theoretical simulation, taking care of this. And what was your second question?
So my second question is that, so in my research purpose, so I'm trying to make a laser by using a nanotube. So is that possible by any GaN device or by using 3-5
Ideally, nothing is impossible. And the most interestingly, so far as the theoretical study is concerned, you can consider anything. But when it comes to realizing it, but even if it is a theoretical simulation or design, I must keep in mind that how I'm going to realize it in the lab is really very, very challenging. I will not say no, it is not possible, because you know that latest VLSI technology, what people are doing, that instead of using the traditional MOS structure, they are using carbon nanotubes, or they are using graphene also for making your integrated circuit. And IBM and Stanford University, they have been successful in realizing in IC based on that. So I'll not say it is impossible, but the technology may be involved. But another important thing which we need to keep in mind, that whatever you suggest and show theoretically through simulation, industry may not be ready to take it immediately, because the cost involvement is also very, very important. Right, the industry will like to put money where they will have immediate return, right? And so cost of technology, this is very, very important. That's why there are a lot of suggestions for getting improved performance of the existing MOS-based ICs, but they are not taken by the industry because of this. This will enhance the cost of the devices. But I suggest that you can try devices. MOS2 is being studied, two-dimensional structure. So that is one area people are trying. Carbon nanotube, definitely. Why not? And because of this carbon nanotubes, this length to this surface area, the detector, they are very, very effective as your gas sensors and other detectors also. They can have huge applications. But again, I'll have those who are doing research particularly, we have to be very, very careful in using the simulation tools. Because the simulation tools are made in such a way that where these restrictions they are put, you do not know. Unless we go to the back end and see that real transport equations they have solved. And some places you will have to go for quantum mechanical analysis involving Schrodinger wave equation also and solve it to get a real simulation. But the tools are designed in such a way you give any parameters, it will give a characteristics which is expected characteristics. But many of these things will not really hold. So in this kind of analysis, it is better to write your own model equations and do it. It is always better rather than banking only the simulation. And because no one will buy it, even if it is sent into journals, they will not accept it unless it is verified by some kind of analytical treatment or experimental results. So that's the risk associated with it. Right. So some kind of physical modeling, mathematical modeling, you have to do yourself. You have to write your own algorithm and do a modeling of the device.
Thank you.
Sir,
Any
I have a
other
question, sir.
undergraduate student? All silent?
Sir, I have a question, sir.
Yeah.
Okay.
Sir, I don't know how much it will be relevant because it's a preliminary questions usually comes to my mind. Everywhere we are talking about solar cells, and we talk about the electrical properties of the solar cells and study of solar cells with the features of electrical aspects. Sir, will it be relevant to study solar cell with in perspective of optical characteristics?
Okay, thank you. It's a good question. And first thing which I tell all the students, please do not hesitate in asking question, even if it sounds stupid initially. Right? Don't do that. Then you'll not really learn. Right? Ask any question which, even if you feel nonsense, and then never think that what the other your fellow students will think. Never shy away from asking question. Do that. I appreciate that you ask this question. Solar cell, you know that the main reason that why people are focusing on solar cell is that fossil fuel life is limited. You are not going to get it abundant supply of fossil fuel. So you'll have to look for alternative source of energy, right? And you may argue that nuclear energy may be one alternative, but you know that other consequences of using this nuclear power plant and the other related issues. So that abundant energy we get from solar energy is obviously we should try to tap that. And why only solar energy? Wind energy, this is another, right? Hydroelectricity, we already use it, this. So all kinds of, not only that, even in the energy we spend in typing the keyboard, the energy we spend in flexing and deflexing muscles, not only human being, animals they are doing. And that can be a source of energy. And this kind of mechanical energy through a piezoelectric crystal can be converted into electrical energy and can be used. You will have to look for alternative source of energy. And that's the future answer to this energy problem that the whole world will be requiring. And so we talk of energy harvesting. So energy harvesting will not be something which you generate energy like electricity you generate and then you have a transmission and distribution system through it, you distribute it. No, at the local point you generate it and supply and cater to the needs of your electronic circuits there itself. So at that point you have to generate that energy, that kind of energy harvesting you have to look for. And definitely, so solar energy, we will have to use solar energy and we have already started using, and the large section is now banking on whether it is heating your water or getting light or multiple functions now we are getting from solar energy, and it has a very bright future. You know that even though the major share of the market is photovoltaics market is by single crystal silicon solar cells, but these new generation materials which I mentioned, including these organic semiconductors, are coming in a big way because some of these materials are very cheap materials. And large area solar panels can be created by using these organic semiconductors, and they have already come into market, and many African countries they are using these solar cells which are based on your organic semiconductors. So solar cell, there will be no substitute, and there will be progress daily. Every day you will find that new generation solar cells are coming, perovskite solar cells are coming. So a lot of researches are going on for improving the efficiency. The main problem of tapping the solar energy and converting it into electrical energy is that the solar sun is emitting photons of energy in a band which is very, very wide band. And all of this energy cannot be tapped by our device. And that's why the efficiency of the solar cell is very, very good. Right. So something around 20% or little more than that with complexity of this design we have achieved. And so our focus is now to increase the efficiency of the solar cell more and more. And solar cell is going to stay, and that is the future answer to this energy crisis which we are going to face in the near future. So it is a part of optoelectronic device definitely, but it has expanded in such a way it itself has become a branch separately. Now we do not call this optoelectronic solar cell as separately as a part of optoelectronic device. It is a field in itself, solar cells, right? But optoelectronic devices focus more on other applications that how electronic devices can be modulated by optical properties to be something done by light. Right, there will be devices which will be coming where the electronic device performance, say you have an electronic oscillator, and that oscillator frequency you won't have to change by changing the lamp parameters of the circuit. I'll shine light on this device, which is a light sensitive device, and the frequency will automatically change. So you'll have a virtual kind of gate in a transistor, field effect transistor based oscillator, where the light can change the frequency. So it is a huge opportunity in optoelectronic devices. A solar cell per se is becoming a entirely a field of its own, right? Which needs a lot of development. But, yeah.
Sir, I have another question, sir.
Yes.
Sir, what are the basic differences of the challenges in between the optical signal processing and electrical signal processing, sir? Sir, am I clear?
Yeah. I think that's a very good question. Very good question. You know that from the analog signal processing, we came to digital signal processing only because of the fact that we can take help of the computer to do a lot of processing, which you used to have the hardware design first for analyzing the signal has been done away. And since with the advent of this IC technology, the VLSI coming in, the computers have become cheaper and cheaper. Once upon a time, it used to be a central facility for an organization, has now come to your pocket, as in the form of smartphones, right? And this huge flexibility and analyzing this in the digital form, converting it into the machine language which the computer can understand, the processing has become very easy, and that is the reason that why the digital signal processing. Now, signal processing essentially means digital signal processing. But if you can go to the optical signal processing, you can imagine the kind of speed you will be getting in the processing of the signal, which can be much faster than the digital signal processing. Can you know why we say so that if we go to optical domain, it will be very fast? I started with this lecture saying that when you come to the electrical domain, your bandwidth is severely compromised. Right? The velocity of light, this is the maximum velocity which you can get 3 to 10 to the power 8 meters per second. Compared to that, the velocity of the electrons which you go through a semiconductor is 10 to the power 5 meters per second. Right? And the transit time, the time it takes to travel the distance of the device from one terminal to the other, that actually limits that what is the highest frequency at which this device can operate. But when it comes to light, so that will be in the lightning speed. You can say that's the highest speed you can imagine. That's why I said that typically the frequency you are handling in your microwave is 10 to the power 9. That's a straight jump of frequency by 10 to the power 5. So that gives you an enormous value. So this kind of data, huge amount of data can be handled in very short time if you can do optical signal processing. But for making this optical signal processing possible, all this digital counterpart of these devices like logic gates and all these things have to be obtained in optical form. And that's a challenge. Some devices are available, and we need to design some more devices so that optical processing becomes affordable. Right. Yes. Any other question?
Sir, no, sir. It's wonderful to hear from you for your energetic and so detailed analysis of optical devices and how it can be constructed from the basic level to the current research domain. You have explained almost the basics of all these things. So, sir, we are very glad to hear from you. Sir, we need to take one photograph with you, sir, if with your kind permission.
Yes.
Sir, all the students are requested to just on their video so that we can take a photograph with sir. With our respected sir, we can take the photograph. All participants are requested, please, on their videos. Sir, we will surely hear from you again, sir. We are so much enlightened with your lecture and so many questions we have actually to ask.
You are welcome. You are welcome, and let me know. I will have the lecture sometime. Right, but you should encourage the students to ask more and more questions. I tell
Yes,
you for
sir.
the
Yes, sir.
students' information, this is very exciting area of the electronic device, and it has a huge future. Those who are planning to have
Actually,
higher studies in
sir,
this
actually,
area,
sir,
yeah.
Sir, actually, the students are facing difficulty to ask you because in previous days in our markout syllabus, we have optoelectronics from the very beginning. From the basic electronics, we have a part of optoelectronics. In the solid state devices, we also have a part of optoelectronics. But now these optoelectronic devices has become a program elective, and most of the students avoid to take the optoelectronic devices subject because the optical communication part there is rarely to understand if they don't know the very beginning or the basics, so they fear to take that subject. So other subjects which are more easier than this one, they used to take that subject. So for this reason, sir, they actually have the basic idea but don't have the idea what you have told, just that part they have not covered in their syllabus. So that's it. That is the reason the students are not asking you questions. But if we meet again, sir, we must take our preparation so that we can have lots of questions to ask you, sir. So we are taking a screenshot. Thank you, sir. Thank you for your valuable time. So,
Okay, so I can leave now.
yes, sir, you can leave now.
Namaskar.